Hello, pre-calc honor students. Here we are with 11.1, polar coordinates and graphs. Here's one of the applications of polar coordinates. Radar stands for radio detecting and ranging. And we'll look back at this in a second. But here's our objective, to graph polar equations. So first we got to think about points in polar. A point P in the plane can be described by giving its directed distance from a fixed point O called the pole. So here's the pole. And we can have a certain directed distance, like let's say this is 5. And we've rotated the measure of an angle formed by ray OP. Here's the point P. And a reference ray called the polar axis. So here's your polar axis. And normally we put the polar axis along the positive x-axis. So this would be 5 at an angle of, let's say, 40 degrees. So you could say 5, 40 degrees. Now we could also label it this way. We could say, oh, we could go all the way around this way. So we could say it's 5 at an angle of negative 320 degrees. Backing up like that. And so notice how these all ended up on, this is an example polar graph paper here in this blip screen. And let's label these 1, 2, 3, 4. So this ends up being 1, 2, an angle of, it looks like this is 0 degrees. And if this is 90, how have they split this up now? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Every 15. So this is 15, 30, 45, 60, 75. So this point in here is 2 at an angle of 45 degrees. Okay, let's label this point down here, or up here. 1, 2, 3, and the angle it makes with the polar axis here is actually 120. 3 at an angle of 120 degrees. And this one's 2 at an angle of, looks if this is 180, 210. You see that sometimes I actually put the little angle marker in there. Either is acceptable. And here, this looks like 1, 2, 3.5, 3.5 away from the origin. And the angle is, if this is 270, this is 285, maybe 290. Notice you might have also just said 3.5 at an angle of negative 70 degrees. Taking it down that way. Okay, let's look at some more. Let's plot these points. 6 at an angle of 30, and we can actually plot the points, and I'll move the labels over. 6 at an angle of 30, so here's our 30 degrees. This is again set up like I did before. This is every 15 degrees. So 30 degrees, you can set up your angle first. Count out 1, 2, 3, 4, 5, 6. There's your 6 at an angle of 30. 4 at an angle of 150. Here's 150. 1, 2, 3, 4 at an angle of 150. 8 at an angle of 225. Here's 225. 8 at an angle of 225. 1, 2, 3, 4, 5, 6, 7, 8. 10 at an angle of negative 30. Where's negative 30? 10. 2, 4, 6, 8, 10. Again, let's move all the labels with those. 4 at an angle of 150. 6 at an angle of 30. 8 at an angle of 225. Okay. Directed distance. See, all the lengths were different and the angles were different. Now let's try this one. 6 at an angle of 30. Wow, a lot of variations on this. 6 at an angle of 30. Well, we already plotted that already. We said it was up here in the first quadrant. 6 at an angle of negative 30 is going to be down here in the fourth quadrant. Negative 6 at an angle of 30 is actually in the opposite direction. Now this is tricky. You can actually give a negative r. It's like you're setting up the number line along the 30 degree axis here. And here's negative 6 at an angle of negative 30. Let's see how this works. First of all, I'm going to put a nice straight line in here, right at the 30 degree level here, right like this. Whoosh. There's our 30 degree line, okay? And so this is, and let's get that back on top there. Where is 6 at an angle of 30? It's out here. 1, 2, 3, 4, 5. I'm sorry, 1, 2, 3, 4, 5, 6. There's 6 at an angle of 30 degrees. Because I've taken my little ruler and gone 0, 1, 2, 3, 4, 5, 6. So think of your ruler going this way too. -1, -2, -3, -4, -5, -6. So there's your -6 at an angle of 30 degrees. So this negative number on the range, on the R, is actually going to put you in the opposite direction. So that's what happened here with 6 at an angle of -30 down here. Oopsie, let's get it on the right circle here. It's actually right here. Yeah, I forgot that -1. This is -1, -2, -3, -4, -5, -6 right there. Clean that up a little bit with the micro eraser. There we go. And so then here's 6, -6 at an angle of -30. Notice this is the -30 direction this way. So if I go -6 and -30, you're up here. Okay, I hope that helps. Now sketch the polar graph of r equals 2 cosine theta. This is first a rectangular graph. I'm going to start with this because this is what you're used to. You're used to saying from 0 to 360, 2 cosine theta is going to peak at 2 and down at -2. And halfway through, let's see, in quarters, 90, 270, and it'll go mama, max 0, min 0, max. And here's your cosine graph, right? But now each of these corresponds to a point. Even though I just plotted 0, 2 here, and 90, 0, I'm going to write it as 2 at an angle of 0 degrees. And this is 0 at an angle of 90. And this is -2 at an angle of 180. And this is 0 at an angle of 270. And this is 2 at an angle of 360. So now when we start plotting these, and I'm going to have this be 1, and this be 2 out here like this, just so we fill up the graph paper a little more. We've got 2 at an angle of 0, then 0 at an angle of 90 here, and then -2 at an angle of 180. Well, here's 180, but the -2 at an angle of 180 shows up here as well, as 2 at an angle of 0. Those are both actually the same point. 0 at an angle of 270, that's the pole again. Anything with a 0 is just basically right at the pole. And 2 at an angle of 360, oh, I did that one already. That's back to this again. So all we've got is 2 points. Let's get a few more. Let's make a little chart and get a few more points to plot here. Here's our angle theta, here's R, and here's angle theta. We're already seeing that 0 goes to 2, and that 360 goes to 2, and that 180 goes to 2. In fact, we repeat everything a lot here. Let's see what happens and 90 we said went to 0. What we want to do is find out a little more about what's going on in between a lot of these things. So let's try 45 degrees. 45 degrees, remember it's R equals 2 sine, or cosine, right? Cosine, 2 cosine theta. So at 45 degrees, we get the square root of 2 of 2, so we get the square root of 2. So at 45 degrees, square root of 2, which is 1.4, like that. Wow. What happens at 30 degrees? Cosine of 30, square root of 3 of 2, you get square root of 3. 30 degrees, we get square root of 3, that's 1.7, somewhere in here. What happens at 60 degrees? That's a half, so we get 1. So we get 1 at an angle of 60 degrees. Here's 60, there's 1. And sure enough, what you get is a circle. We put some of those other points in, and it actually overlaps it twice. And now let's see what happened over here. Basically, this formed a petal here. We started at 2 and we got down to 0. And while we're sweeping through that, we basically started here and swept in here like this. We got down to 0. Now, this is why 90 and 270 are what I call polar guides. Anything where the R is equal to 0 are polar guides. So I actually put a little dashed line like this at 90 and 270. It tells me not to cross there because that's where the curve is going to come swooping in toward the pole. And that's what it did. Now notice what happens when we went into quadrant 2 here. So this was quadrant 1 when we drew this. When we're in quadrant 2 now, in this little section, in quadrant 2, this is quadrant 2 up here. But we had all negative answers, so they got pushed into here. Exactly the opposite direction from quadrant 2, actually into quadrant 4. And then when we jump to quadrant 3 here, this stuff that was normally in 3, again, is negative, so it actually flips up here and starts drawing it again. And then this quadrant 4 stuff, which should be down here, does stay down here because you have positive R values. And that's why it kind of overlaps itself. And we don't get anything over here in quadrants 2 and 3. We'll try some more examples of this, don't worry. It's tricky stuff. But before we get to that, let's get to some polar and rectangular conversions. Basically, our old way of doing things was giving the x and y coordinate of a point. So here we go. I've got the x and the y coordinate of the point. I go over x, oopsie, go over x, and I go up y, over x, up y. That's the rectangular coordinate system. That's how you plot points in the rectangular coordinate system. But when I'm in polar, you figure out the angle and you go that much distance. You go r at an angle of theta. And so now we can start working on the conversions between these two. For converting polar to rectangular, if you've got r at an angle of theta, like that, also known as r comma theta, or r semicolon theta. I've seen it presented all those ways. To change it into rectangular, we can do our work with SOHCAHTOA. Remember how the sine of theta is y over r, and the cosine of theta is x over r? That means y equals r sine theta, and x equals r cosine theta. What handy formulas. That's it. That's converting polar to rectangular. X equals r times the cosine of theta. Y equals r times the sine of theta. There's a handy formula. I also want you to be able to convert from rectangular to polar in next chapter, just looking at the picture sometimes, especially if it's a special angle. Now converting rectangular to polar. Now we start with the x and y coordinates. How do we get y and r? Well, remember x squared plus y squared equals r squared from the Pythagorean theorem. So r is the square root of x squared plus y squared. I don't normally say plus or minus because I want you to give me the positive value for this. And then the tangent of theta equals y over x. And right now I'm just going to leave it like that. Tan theta equals y over x. Because when you go theta equals the inverse tan of y over x, remember that's only going to give you an answer between in the first or fourth quadrant. You might want to have something in the second or third quadrant. So you might have to look at the angle, this angle, or something 180 degrees away from it. So give polar coordinates to the point 3, 4. Let's just make a picture. Oh, that could be better. Here we go. Over 3 and up 4. That's 3, 4, and we want to come up with the polar coordinates for this. So r is the square root of 3 squared plus 4 squared. We get r equals 5. And the angle, theta, tangent of theta, equals 4 over 3. So I'm going to go inverse tangent of 4/3 and get 53.1 degrees. So the polar coordinates for this is 5, 53.1 degrees. Now give rectangular coordinates for 3 and angle 30. Okay, so let's set up another set of axes again. And set up 3 at an angle of 30 degrees. Here's 3 and this is 30 degrees. So we can quickly convert with the r cosine theta formula. 3 cosine 30, 3 times square root of 3 over 2, and so we get 3 square root of 3 over 2. And our sine theta for the y coordinate, 3 times the sine of 30, 3 times a half, and we get 3 halves. So we get 3 square root of 3 over 2, comma 3 halves. Now you could have also just set this up as the most beautiful triangle in the world. Say, hey, this is a 30, 60, 90. 30, 60, 90, the short leg is exactly half the hypotenuse, and the long leg is the square root of 3 times the short leg. So there's your x and y coordinates. Now sketch the polar graph of sine 2 theta. Okay, so a little more practice now sketching polar graphs as promised. Here we go. Let's go from 0 to 360. And I'm just going to label this, make that black. It's 180, 90, 270. But now since it's 2 theta, it's 2 on the outside, so we're going to go up to 2, down to negative 2. And since 2 theta, we're going to do a complete cycle of the sine in 180 degrees. And then we have a whole other sine cycle here. And it's important to do both because in polar graphing, you want to go all the way from 0 to 360. You want to run the gamut. And we're going to come up with a bunch of points here. We have a bunch of polar guides. We have polar guides at 0, 90, 180, and 270. These are basically when the r comes into 0. And so I'm going to actually label those and put dashed lines in there. And let me get some better dashed lines here for our polar guides. There's a polar guide, and there's a polar guide. Okay? Get lined up precisely. There you go. Oopsie. Precisely. There you go. Now I'm going to graph some of those key points. That is, this 2, oopsie, 2 at an angle of 45, and 2 at an angle of, looks like 225. So I'm going to call this, let's call this 1 and 2 for my scaling. 1, 2, 3. Yeah. And 2 at an angle of 225. 2. And we also have here negative 2 at an angle of 135. Now check out where this shows up. Negative 2 at an angle of 1. This was 2 at an angle of 45. This is 2 at an angle of 225. Negative 2 at angle 135. Here's the 135, but negative 2 will actually be down here. Negative 2 at an angle of 135. And this is negative 2 at an angle of 315. 315 is down here. Negative 2 at an angle of 315 degrees. 315 is down here, but negative 2 is going to put it back up here. So this is negative 2 at an angle of 315 degrees. That's that negative magnitude coming into play there. Essentially what happens is we're going to get 4 loops on this. And just get your loops in the right direction. Watch how I draw this. And you can also watch your calculator do this too, and you can see it happening as you go from 0 to 360. So here we go. Here's section 1. I'm going to call this Roman numeral 1. Actually, I'm going to call it big A. And in big A, we go from 0 up to this peak and then back down to 90. So it loops along like this. And there's A. And it'll actually draw it in this direction. Then when we get to B, from 90 to 180, it's actually not going to continue this way. It's going to continue synergies like this. It's going to come swooping down into here and do this next. Because B is negative. And so the pedal shows up in the opposite direction to this 90 to 180 quadrant. So instead of quadrant 2, it ends up in quadrant 4. Then let's look at C. C is from 180 to 270. Now we're back to normal positive R's again. So that's why C loops along here like this. And then for D, 270 to 360, which would normally be down here in the 4th quadrant, we end up going in the opposite direction like this. And we pick up from where we left off then. So it's good to watch it on your calculator as well. And you can see the magic of this, these directional changes and so forth. And so you get 4 pedals here. which is kind of confusing because here we got 4 petals, but when we did the other one, we only got 2. When I did that first graph, we only got 1 petal, even though there were basically 2 petals here. This 1 and 4 combined to make 1 petal, and there's another petal. Well, in this case, they exactly overlap, and the 2 petals overlapped each other, so it only looks like 1. So that's why it's important to find out where does your normal graph equal 0. Try it on your 89. Now remember, go to mode and change graph from function to polar. And now the y equals menu will have r's in it, and you have to use a theta. And the theta you can get from that, it's right above the caret, and it's in yellow. Here's example 4. Find a rectangular equation for this. Well, we can use all our conversion factors. That is, r equals the square root of x squared plus y squared. So we can replace r with the square root of x squared plus y squared. But that's going to be kind of messy because of this sine 2 theta thing. So, and we've got sine and cosine. So I'm going to just suggest something first before we go plunging into these. And that is, try and get rid of this trig function first. Here's why. I look at this as r equals 2, and then sine 2 theta is 2 sine theta cosine theta. So I got r equals 4 times the sine of theta is y over r. The cosine theta is x over r. See, so now we got the x and y's that we need from rectangular coordinates. And now I can multiply both sides by r squared, so I get r cubed equals 4xy. And now just put in square root of x squared plus y squared in for r. And there you go. That's fine. If you want to square both sides to make it even bigger, be my guest. If we square both sides of this, in other words, square root of x squared plus y squared cubed squared equals 4xy squared. So we get x squared plus y squared cubed equals 16x squared y squared. There, you can try entering that in GeoGebra. It doesn't really take the nose so well. I did find some applications for GeoGebra that some people have worked out some programs, but I can find the polar graph paper on GeoGebra, but not the polar graphing itself. Here's an example, though, I found from a website where I looked at several ones. And here's 1 minus sine 2 theta quantity squared. R equals 1 minus sine 2 theta. That whole quantity squared. And you get some interesting effects on this. And if you look at your R graph as a function of theta, remember you're going to get sine 2 theta. This is going to take a whole other little analysis here. When we start with sine 2 theta from 0 to 360, we get 2 sections, right? Now you're going to take the opposite of that, raise it up 1, and this is going, so it's going to just touch down here like this. Like that, right? There's one cycle, there's another cycle. Yep, so it's always positive. Now when you square it, this 0 will stay here. So when your final step of squaring it, these stay at 0. This 1 will stay at 1, won't it? This 1 will stay at 1. I'm sorry, that's 2. That'll jump up to 4. That's where we get up to 4 here. 4. These ones will stay at 1. Because 1 squared is 1. So your graph stretches out a little bit. And so we get this petal. We get these 2 petals. See how the petal goes over here? 2 really long petals. But notice where the petal starts and stops, though. At the polar guides here, which are here and here. Your polar guides are at 45 degrees and at 225 degrees, separating these 2 big sections. Okay, here's 4 sine 3 theta, and we just get 3 petals. Notice when I go to 4 theta, I get 8 petals. What the? And 5 theta, you're back to 5 petals. And 6 theta, you're up to 12 petals. So notice the pattern there? Tell me about it in class. How can you predict the number of petals based on the multiple on theta? Okay, flange out.